Good morning to everyone. I'm Naman. I'll be presenting my work on how can we learn some models for robots directly from raw robot trajectories that can be used to plan using them. So let's see. Yeah, okay. As a roboticist, what I envision and what I think everyone in the room would want is robots should be present everywhere doing tasks for us that are dull, dirty, or dangerous. So, for example, for me, at least, loading up the dishwasher is really dull, and I would really want a robot to do it for me. But we are not at this stage yet. And one of the reasons we are not at this stage yet is the topic of this workshop, that's generalization. Uh, the current approaches that we have been seeing maybe in past 1 year about robotics coming mainly focus on something called behavior cloning or imitation learning, where people use teleoperation to collect a lot of training data and then try to learn a neural network that uh, sort of predicts what action to take for these particular tasks. But there are pretty much obvious limitations on these things. So one of the limitation is it requires really, really lot of data. So most of these approaches requires like 5,000 demonstrations for each task. Even after these 5,000 training demonstrations for each task, what the coverage they get over the training task is just 75%. And then forget about generalizing that to any new test problems. So they can't increase the number of objects. They can't really change where the objects are placed in the training tasks. So they don't really generate to these out of distribution tasks. Even tasks seems to be in distribution. So what we really want or need in this case is, can we collect only a few demonstrations on very simple training problems, which include very low number of objects, which include very simple tasks, and then do something with that so we can solve significantly complex problems. We can generalize to significantly complex problems that has more number of objects, different goals, and etc. Luckily, uh, we as humans show these capabilities, and we are lucky to have us around to get inspiration. So humans can do these tasks very nicely. Why? Because we have some things that robots typically don't have. We know attributes about the object, so whether a dishwasher is closed or not. We still know the relationships, like whether object is inside the dishwasher or not, and we know actions that if I want to wash dishes, I have to keep objects in the dishwasher. We take these for granted, and also, with our luck, there are existing algorithms, very nice algorithms, that can use this information. So it can use these symbolic relationships and actions and how to perform these actions and do these tasks using robot. So the question that I posed before, that can we do something, can we learn something, can we do something with the low level demonstrations, very easy demonstrations? So the idea basically simplifies is to, can we learn all these information, what I call a model, that is the predicate, action, preconditions of these actions, and how the robot can execute these actions at the low level automatically from this training data. And that's what basically this work focuses. What we use is something we call critical regions. They are generalization of bottlenecks and hubs in the configuration space of the robot. Basically, the numerator computes the hubs, which is easy to access areas, in the sense that from there I can access a lot of things in the environment. And the bottlenecks is something that which is very hard to sample. And when we combine them into a single definition, we get critical regions. Uh, so here is one of the demonstrations where the gripper is picking up an object. And if you see, if I have two gripper at different locations, object at different locations, I don't really get any information from that, from the trajectories. But if I put these trajectories in the relative frame of the object itself, now I have something informative there. So, and this yellow region over there becomes a relational, what we call a relational critical region. Relational because it is in the relative frame of reference of the object. And these relational critical regions we use to define symbols between objects, or relations between objects. And then actions for the robot becomes transitions in and out of these symbolic relations. With that, here is an overview of this approach. So basically, we start with a few training demonstrations. We convert those training demonstrations into relative trajectories to the objects, or different objects in the environment. And from that, we synthesize a generative symbolic model. And we do these action invention, which goes in and out of critical regions. Once we have these things, we can easily generalize to multiple objects in the environment and different goals for those objects. So we carried out some empirical evaluation. We mainly focused on these four parameters of evaluation and how generalizable, how robust, and how succinct these representations are. So we did it in 5 different domains. One of the domains where the robot is delivering items in a cafe. So, the second one is where a robot sets up a dining table. Third one, where the robot uses Kiva planks. I'll be showing results for each of the domains, but that building uses Kiva planks to build structures, and then the same concept but with Jenga planks. And lastly, we have a very small box, and robot has to tightly put things in the box. The second and the fourth one we actually implemented on a real robot. So here are some videos from some of our experiments. So on the left, what we are seeing is a training video. So we had, for this domain, we had 6 training tasks. Not more than 3 objects were involved in this training task. And once we learned models from these 6 training tasks, we were able to solve problems that are on the right, which had significantly more objects and significantly complex structures were involved here. Okay, going further, we had similar task, but now we are in the real world. So on the left, we show how we collected data in the simulator, and then we do sim to real transfer. And similarly, very small number of objects on the left, but we generalize to up to 18 objects in the real world, with training data just coming from the 3 objects. And again, one of the domains where we collect the training demonstrations in simulator just to pick one object, and then we generalize it to the real world with 4 glasses and 4 cups. And here the robot is setting up a dinner table for someone to eat. Okay, this video might take some long, but I can just fast forward it and see to the end that the robot is placing the things on the table. The last domain, we had to pack a box with 4 objects. The training demonstration has only 1 object, and then we generalize it to 4 objects. Similarly, you can see the placement of the object was very tight, so it has to learn really nice relations and how to execute those actions. So here are some of the relations that we were able to learn. So you can see we were really able to learn this, settings where the robot has to be near table, or the robot arm has to be very near to the object to grasp it. Similarly with Kiva planks, we were able to learn what parallel means and what on top means. And a few empirical results, statistical results. So here are the generalization thing. So each bar here shows the fraction of maximum number of test objects to the maximum number of training objects. And we can see while the current behavior cloning approaches stay at 1, we were able to scale it up to 18. Also, the limitation here just was that the task planner failed at 20 objects, and we couldn't go more than 20 objects. Here is how much training data we used, and you can see that we used less than 100 trajectories to learn almost as good a model as an oracle. So here the task and motion planning, that is the stars on the top, are the oracle with human developed abstractions, and we were able to perform almost to their level in less than 100 trajectories for each task. So here you go. Lastly, we also compared with Codis policies, which is one of the VLM-based approach that uses all the internet skill data to generate policies and learn things for robots, but it performed really bad, poor, and even after giving 25 trials. So yeah. Finally, this is the conclusion. So we start with a very low number of trajectories with small number of objects. We learn these action models and relations, and then we can now scale up to generalize to much more complex problems with very high number of objects.
Thank you. We just have time for one quick question.
Meanwhile, I think the spotlight speakers can make a line here.
Please line up for this.
Thank you for the presentation. I just had a quick question. Now you mentioned interesting example about dining table, how robot can set up the dining table. what happens when I change a preference, or I personally have a different preference? I do not want the bowl to be placed next to the glass, but on top of the glass. So for this change of preference, not just in the dining table environment, for any possible environment, how, like, does it need a complete retraining, or can it generalize right off the bat?
Good question. So the thing that I didn't mention here is it's sort of a continual learning approach. So it will try to first solve the problem with whatever knowledge it has. If it can't do that, it will go into this learning phase and it will figure out what is making the problem not solvable, and then try to learn new model for it, and then do the thing. So the preference or the goal is still part of the input. You need to mention that, okay, I want this placement, and if it can't do this, it will go into the learning phase back and learn these new relationships.
Thank you. Let's thank our speaker.